another question there.
So in your slides, you had a couple of examples where your automatic method was making counterexamples that were smaller than the things that people had done by hand before. I was wondering if you thought a bit about anomaly, or if you have any idea of how much smaller those examples might be, or if you're just getting lucky and getting ones that are smaller this time versus the like truly smallest, or thoughts along those lines.
Sure. So the question was, when we found examples that are smaller than these manual generated ones, do we know that these are the smallest ones? Almost yes. So yes, because the way we use alloy is that we start with a bound of 1 and we go 2, 3, 4, and we stop, as soon as we find one. So once we found an example, we know that there are no smaller ones. Say almost yes, because when we impose the dead predicate, we lose a bit of completeness. Not much, but a little bit. And so we can be completely sure that there aren't some smaller ones because of this deadness requirement.
Very well, thank you. So from check-in and bug finding and concurrency, we gradually proceed to verifying concurrency. So what happens if we take a state-of-the-art, very express program logic for concurrency and try to implement it in the state-of-the-art proof assistant, like COG? So the experience is going to be described by Krebbers.
Thank you very much for the introduction. Hello. So yes, so indeed, the problem is there, we have like many complicated program logics have been developed. And the good thing, it's great, that many of those come with mechanized soundness proofs. So the meta theory of these logics have been formalized in a theorem prover, and it's been shown that these logics are indeed sound. But now we want to get one step further. We want to use the theorem prover to actually reason in these very complicated logics, and we want to use the theorem prover to show, using these logics, that our programs are actually correct, actual programs. So how would you like to do that? Well, I like to work in COG, so I would like to work in such a logic in the same style as I'm used to working in COG. And I will show you how to achieve that. So, how? What will I show you how to do? I will show you how to extend COG with spatial and non-spatial named proof context for an object logic. I will show you how to implement tactics for induction and elimination of all connectives of that object logic. And I show that this can be implemented entirely in COG itself. I didn't have to modify COG at all for this. It can all be done with features that COG already has, namely reflection, type classes, and its tactic language, LTAC. There's no need to write any plugin or to modify COG at all. So, for the sake of this research, I had to pick a concrete logic, because, well, now I wrote an object logic, but we may want to use some particular object logic. So what did I pick? I picked the iris logic, because that's quite an expressive, higher order separation logic with a lot of fancy stuff. So by doing that, we can see whether this approach actually scale to something, to an actual cool and big logic. So, to give you an idea of how it works. So we want to prove the following statement in separation logic. This is a very simple statement, but it's just to show you an idea. So we open COG, we use our development, which is called iris proof mode. We type it in. So note that this looks pretty much like what you would normally do in COG. But instead of having normal implication, we write a 1, which is the implication of separation logic. And instead of conjunctions, well, we write stars. So here we have a statement of separation logic that we would like to prove. So we type it in COG, and then we get a wonderful goal, in which we have to prove that. What's the next thing we do? We type in I intros. So note it's like COG, but instead of writing intros to introduce stuff, we write I intros. And what happens after we do that? Well, we get our assumptions that we have introduced here. So this thing here called an introduction pattern automatically eliminates all of the assumptions. So we get P, this thing which you call HP, we get this extension which you call H phi, and we have R which is called HR. So you see here, this is a normal Coq context with all the assumptions from Coq, and these are the assumptions from separation logic. And now, like we do I intros, we can eliminate the existential using I destruct. And what do we get? Ta-da! The existential is being eliminated. So here you see the existential disappeared in the Coq context, the variable appears. Now we can instantiate it. And now we get into something that's more fun. We are in separation logic. So these assumptions here, they are resources. You can only use them once. So if you want to introduce the separating conjunction here, we have to decide which resources are we going to give to the left and which resources are we going to give to the right conjunct. So for that we use the I-split L tactic, which means split introduce the separating conjunction by giving this resource here to the left-hand side and all remaining ones to the right-hand side. So we can do that, and then we get two goals. As you see, the context is split up in both goals. And proving these will be simple. We do I assumption for that, for the first, and for the second, we do I assumption. So note here, this thing is exactly like a proof in Coq, with one big difference. It is not the Coq logic, this is in the iris logic, and we are doing spatial reasoning. So now you may wonder, how did we do that? So I will now give you a teaser, and during the talk I will go into a bit of more detail how I did do it. So this thing here, it's all fake. It's just a bunch of notations for an embedded logic. Interesting part. The more interesting part is that if we go to this part in the proof area and introduce some stuff, we see this context. It's in fact also fake. Just a bunch of notations for a deeply embedded context. So if we do unset printing notations, which disables Coq's reprinter, then we enter with something like this. So here you see all the ASCIIs, they correspond to individual ASCII characters, they represent the names, and just a bunch of association lists that are being pre-printed something fun. And all these tactics around it are programmed such a way that they manipulate this association list that's being pre-printed, just to give you the kind of experience as you would normally have for working in Coq. So, of course, there are some people that will be like, why would you care about interactive proofs? I mean, interactive proofs are the kind of stuff that they do in the 90s. We should automate everything. I don't really believe that statement. There are a large class of programs which we can automate and which we should automate, but it's not feasible to automate everything. So we have a lot of examples already. So we have this iris proof mode now for like a half year or so, but we have already various examples in it, and it's quite unfeasible any of those can be automated. And all of these things, they really make use of all kinds of tricky connectives of iris. They make use of all kinds of nested ones and predicative invariants. They are not the usual Hoare-style proofs. So, to note, many of these projects, they are formalized in IPM, iris proof mode, or they are being formalized in IPM. So, this shows that this approach appeals to something more than just proving a want. So, but how to do such proofs in proof assistance? So people have already been taught about this. So there's been quite some work on having all kinds of macros for manipulating Hoare triples, like do symbolic executing, framing stuff, pulling out existentials. So that goes back to pretty much like 11 years ago, I think, when Robbert and others, and there have been various variants of that. Then all kinds of people have been trying to automate that with impressive results like Bedrock that can automatically verify Hoare-style specifications for quite cool programs. However, the domain that we are in here with this, is a bit different, because iris many, it's way beyond Hoare logic. It's not just proving Hoare triples, as I already said, but emphasize that yet again. We really have like all kinds of modal connectives and invariants and so on, and we want to support that. So to that end, we really want to have interactive proofs, and we want to do that in Coq because we don't trust ourselves. So let me first try to explain how one would typically embed a logic in a theorem prover. There are two typical ways of doing it. One is a so-called deep embedding, and the other is a so-called shallow embedding. Whenever you have a deep embedding, then you really define like an explicit syntax for the formulas of your logic. Like here we have an inductive data type, and then we have a connector for AND and for all, etc. In the case of a shallow embedding, you don't define an explicit syntax, but instead of that, you define your type of proposition as being something semantic, like, for example, predicates over states or something like that, or step-index predicates over step-indexed resource algebras, and then you define all your connectives semantically. So in which case, which of the two should we use, and which is the better? Well, there are various reasons why the deep embedding is great. So the first thing is, since your formulas are just inductive data type in Coq, you can just write functions in Coq that manipulate these things. You can really write in Coq a function that does the framing in these formulas and all that, because, well, they're just data types. And these functions are typically quite fast, and it provides a very powerful mean of having this kind of reflective tactics. So you can prove such a function sound, and then you can base a tactic on that. On the other hand, in a shallow embedding, that all gets much more tricky, because, well, all these things are semantic objects, so it's not just an inductive data type for your formulas, but you can traverse these formulas on the meta level, and you can do manipulations there using tactics. But it's generally much slower. So why not do a deep embedding? Well, obviously, because there is a trade-off. So a problem with a deep embedding is that, well, you have to encode binders explicitly, and that becomes pretty tricky because, well, we have to choose whether the binding indices, whether names, etc., etc. I don't want to do that. Also, here we have the quantifier, and we are doing higher order logic, so whenever we want to have lists, then we also need to put lists as part of our formulas and natural numbers, and all that stuff, we all have to embed that. On the other hand, in the shallow embedding, well, our quantifier, as you see here, it's just a function. So we can just reuse the binders to meta logic, and we're very happy because we don't have to care about this issue of binders. And also, we can just piggyback on all kinds of features like lists and so on from our meta logic, from Coq, because here this thing is just an A, it's just a type. And since Coq itself is imperative, we can put IPRO in there and we can get all the fancy or the quantification we like. So, and there's another trade-off. The other issue is that if you look at the deep embedding, once you write this inductive data type, your logic is fixed. You cannot add other connects to it. Where in the case of the shallow embedding, you can just define other connects, give them a semantic interpretation, and you can really grow your logic if you wish. So, what's the approach that we are going to take? For many of these tactics that I just showed you, like introducing, eliminating, and all that we want to do in our embedded logic, the main thing that we want to do is manipulate the context. And to that end, what we are doing is we are deeply embedding the context in IPM, but we're shallowly embedding the logic. And that way we can write all kinds of reflex tactics to do the context manipulation, which is extremely fast, but we can still use the shallow embedding and use all of the cool features of the shallow embedding, like reusing binder of Coq, because I really don't want to do binders. And we can piggyback on features like this, we get high order quantification and productivity and all that stuff pretty much for free. So, well, as I showed you in one of the early slides, this is how a goal looks like in IPM. So this part here is just the Coq context in which we have all the variables and pure Coq hypothesis. Below that, we have actually two contexts. I only showed you one. One is the persistent context, and the other is the spatial context. So the spatial context contains the things that are really like resources that you can only use once. But the persistent context contains the hypothesis that can be duplicated. They enjoy a slightly stronger property, but it doesn't really matter for this talk. So the nice thing about that is whenever we are using tactics like introducing a separating conjunction, we only have to tell how to split spatial context, because the persistent context can just be split because they enjoy that property. So as I said, all this stuff is fake. It's just a bunch of notations for having deeply embedded association lists of formulas. So the actual goal, if you disable pretty-printing, is just like this. For the people that would wonder how I tricked the pretty-print of Coq into doing this, zero-width Unicode whitespace. Because all notation in Coq need to be parsable as well, and there are some that aren't really, but you can make them parsable by inserting zero-width whitespace. So, like I said, we deeply embed environments. They are records of two association lists. So this is the association list corresponding to this persistent context. And this here, the second component of the record, is a association list corresponding to the spatial hypothesis. And the elements of the association list are the shallowly embedded propositions of logic. Then we can define the interpretation, which is saying something like, well, the environments should be well formed, all the hypotheses in the persistent context should hold, and all those in the spatial context should hold. And this funny modality is to ensure that we can indeed split all these things. And then, how does our goal look? Well, the interpretation of the environments until the actual goal. That's the general setup. So, this thing here is the folded separating conjunction, because, well, there are association lists. So we call the split tactic. How did that thing work? We have a goal like this. We want to introduce a separating junction. Then we say something like I split L, and the context will be split in two. How does this tactic look like? How has it been implemented? It is just lemma in Coq. So what do we say? So we want to prove that in some environment, remember it's a deeply embedded environment, we want to prove Q1 and Q2. Well, then we have to split up the environment into two parts and prove both parts. This thing here, this M splits, is just a function implemented in Coq using some fixed points that splits the environment into two. So the JS, that are the names of the hypothesis that we want to have on the left-hand side, and the LR is whether we want to split on the left or on the right, the Boolean. And it produces just the two contexts for both goals. So now, of course, we don't want to apply this thing by hand. So what we do is we write a small LTAC wrapper around it. LTAC is the tactic language of Coq that basically does do very simple stuff. It applies this lemma, and then we get three goals. 1, 2, 3. The first goal is proving that we can split the context. This is a computable function, so we just tell Coq, compute it. And then we hope that we get a sum on both sides, because this thing can fail whenever some names that appear. And then reflexivity will just do it. In case it doesn't, then it means that we have given names that are not there, and then we produce an error message to be nice to the user so that they don't get some weird error that propagates from Coq somewhere, but instead something readable, so that they actually know why that tactic didn't work. And this is it, more or less. This is how you can embed support for reasoning in object logic in Coq. And possibly in other proofers as well. If people would like to try, I would be very interested in that. So now I will show some more technical parts that are interesting to build up of this. So a typical thing that we want to do in separation logic is framing. So here we have P there and we have P there, and we want to cancel it. So we want to have a tactic, which we call iframe, that does this kind of cancelling. Now we have a bit of an issue, because the goal itself is just a shallowly embedded proposition. We cannot just write a fixed point that traverses that thing. So how are we going to manipulate it? Well, that we do on meta level, using logic programming, using type classes. So we do it, we make a type class that has three parameters. One is the thing that we want to frame, the initial conclusion, and the result. Then we write a tactic by first using a reflexive function that actually takes out and looks up the thing in the environment, then we frame it, and then our resulting goal will be, so P, that's the one in which we are going to frame, Q is the next goal, so Q is the one in which R has been removed. Then there are some tricky tricks, so for example, whenever you try to frame something in the persistent context, you don't have to throw it away, hence the if. So this thing is quite a bit to digest, but the cool thing is that using this type class stuff, we can frame under binders. Users can extend all this stuff by defining their own instances. Whenever you define your own connective in the logic, you can just make an instance for this frame time class. And the frame tactic will also work with your own connective. And we have really seen that in many of the things that we have been working on, because Iris, the core itself is very small, it has hardly any connectives, and we build all kinds of stuff on top of it, and we just define all kinds of frame instances for it, and we can frame in that. So this was a type class, and if you look at the rules for it, it's just a logic program. Whenever we have found the R, then we frame it and it turns into true. Whenever we have a separating junction, we first try framing on the left, and then we replace the result. Or we try framing on the right whenever that thing failed. Of course, we need to clean up too, so we need some smart constructors and all that, but that is pretty boring and straightforward type class programming, which looks a bit scary, but it's manageable. So now I just talked about using it as sort of like a higher order logic, but of course we also want to use it to prove programs. So now we want to prove word triple. This is like the prototypical example of operation logic. We want to prove swap. So we have x points to v1 and y to v2, and after calling swap, they are, guess what, swapped. So the problem is, if we want to do this with IPM, here there is sort of also like the precondition. This is part of the word triple. And what we want to do is we want to pull that out and have that being part of our context, so that we can use our context to manipulate this precondition. So fortunately I'm Dutch. So we had a very nice, very famous and great computer scientist called Dijkstra, and he came up with weakest preconditions. So we are representing word triples in weakest precondition style. So the basic idea is really you just pull out the precondition of the word triple, and it becomes like an implication or a want in front of this. Then there are some technical things like there is this box that's to ensure that the thing doesn't capture any resources. But so how to read the precondition? You should read it as being, well, the weakest precondition under which all executions of E are safe, and so the final state of E satisfies the postcondition Q. All these things are generally best explained by an example, so we have to prove swap in Coq. This is how swap looks. It is some deeply embedded ML-like language in Coq. So we have a temporary, we read x, and in x we put the result of reading y, and then in y we put in the result of the temporary, and we want to prove it in Coq. So we write a word triple. What's the first step? What we do is we introduce the stuff that's on the left-hand side, because in fact, as we have seen in the previous slide, the word triple is just defined as being a want that entails a weakest precondition. So after introducing the stuff, we get the 2 points things in our context, and we get the weakest tree in the postcondition. And now we have implemented a bunch of tactics to do symbolic execution. So this thing here contains 2 lambdas, so we can use the WLET to symbolically execute them. And now the definition has been unfolded. You see that x has basically been replaced by this location. So the hashes are the embedding of literals into our expression syntax. And, well, what can we do now? We are reading from L1. We know that L1 is V1. So we use the WP load tactic to replace that. And now you see all of the temps here. We have a temp there at the end. That temp will be replaced by V1. And there we are. Now we do another load. We do a store. We do a store. We frame the stuff. And we are done. So if you have ever tried to teach OR logic to your students, you will notice that all these protocols that you have seen here, they correspond precisely to the things that you write within basis between all the statements of the program. So this approach really gives you, well, how you would write a whole proof on paper if you would do it in all detail. Of course, this thing can potentially be automated, but whenever you want to do concurrency reasoning, then often around and in between all of these individual things, you want to do all kinds of stuff because you have all kinds of wants and invariants and ownership stuff in your precondition. So there you really want to evaluate it one by one. But in principle, you could write a tactic that does do this, that automates these simple examples on top of IPM. So, okay. I'm going to skip this. So, what's IPM in summary? We deeply embed context, then using computational reflection, we can manipulate contexts. All the tactics are just lemmas and Coq. We need some simple LTAC to turn it into usable tactics and do some error reporting. And using type classes, we can make it more general and we can do other stuff as well. And hopefully these ideas are applicable to your logic of choice. So then there is a paper. In the paper there is a detailed description of the implementation, and we have shown that this scales. So we have applied it to verify some concurrent algorithms like logs, counters, barriers, and that stuff. We have used it to formalize unary and binary logical relations, and that's really the kind of area where this work pays off, because that is very much not standard Hoare logic. It's not proving Hoare triples. It's really making use of all the features of iris to model these logical relations. And we have used it to prove some logical refinement using these logical relations. So, thank you.
We have time for one question, so make it count.
So this is a very impressive piece of work, but from the perspective of what you use in the COG system, what is the will you be able to provide a wish list of all the capabilities that you are using and that you want to be preserved in the future?
This is a wish list of what I want to have in the future, of what I want to. The main thing that I really want is LTAC to be a sensible programming language with a sensible semantics and sensible programming language features like data types, exceptions, and if I would have that, then there are several hacks that can be removed.
Like the no spaces or something like that?
Sorry?
Like the empty spaces or?
No, the empty spaces, that is just a trick, the COG pretty printer. And in fact, since COG 8.6 there's something called, there are printing only notations. They still have an issue, but hopefully that will be fixed someday.
Okay, COG-PL is on Saturday.
Okay, here's a laser pointer, by the way.
All right, so that's the last of this section. As we've just seen, program logics and program logics for concurrency are awesome. So we can embed them in COG. We can verify programs in them. We can prove some cool propositions. But turns out we can do even more. So what we can do is embed type disciplines right on top of these logics. And right now Martin is going to tell us how to do that.
I was. So there was another item.
There's another one.
It was
the wrong one.
There you go.
All right. So types and effects and higher order concurrent separation logic.
Hello, can you hear me? All right. My name is Morten Krog Jespersen, and I would like to present a relational model of types and effects in higher order concurrent separation logic. This is joint work with Kasper Svensson from Cambridge and Lars Birkedal. So, let me see.